here talk with Zhichao Wang on free convolution for probability distribution with unbounded.
Thanks for the introduction. It's my honor to introduce this work with Ethan Davis and David Zhichao. We studied the tree convolution for the probability measure with unbounded spots. This is a generalization of work by Zhichao and Liu. I will introduce later. Okay. So the motivation is to study different kinds of non-commutative independence. Speicher has shown that the classical and free and Boolean independence are the only universal product operation on the non-commutative property space. And later, Muraki showed that the only natural product operations are these three independence plus the monotone and the anti-monotone independence. And our motivation is try to incorporate this kind of non-commutative independence in one umbrella. So that's why we introduce this tree convolution structure to cooperate the free Boolean and monotone and anti-monotone convolutions together. And our work is an extension of this work by Zhichao and Liu, where they observe this operette structure for the non-commutative independence under the rooted trees. And this is a very comprehensive work where they studied this non-commutative independence from 3 points of views. The operator modes, where you can try to construct the free product for the Hilbert space. And you can also, the second one is the combinatory method. You can define the moments and the cumulants to define the independence. And third one is using some complex method, which we introduce the Cauchy transform, K transform, and S transform for the independence. This work mostly based on the bounded operator, where which means they were focusing on the first 2 points of views. And in this work, we are trying to consider the complex analysis, which we can extend the bounded spot probability measure to unbounded spots. So at first, let me introduce some notation for this tree structure we will use later. So we define all the possible alternating strings, which means if you have a string, this Ji cannot be the same as its neighbor. So that's the alternating strings. And we consider all possible alternating strings with the alphabet from 1 to capital N. So that's the infinite many possible strings as a list. And we can use these as all the possible vertices. And then we can define the edges given by this relation, which means if you concatenate with a letter from left-hand side, you define an edge relation between these 2 vertices. So that's how we define the edge. And also, we need to guarantee this JS is still alternating. So you cannot get the JJ at the same time. Okay. So in this way, we define the infinite trees, which we define as this Tn3. So later you will see this free actually just corresponds to the free convolution. So this is the infinite tree, and you can consider all the subtrees from this infinite tree with the same root. Usually we just use this empty set to define this root. So then you can have some finite tree in this case. And we denote the child of this S as all the possible strings JS from this tree T. And conversely, you can define the parent of the JS as the string S. So I will show you a picture later for this thing. So another definition is for the branch of the tree, which we just consider. So for instance, if J is inside this tree, then the branch of this tree at index j is just all the possible string where the concatenation between S and J is inside this tree T. Is the set of all the possible subtrees for this T and free. So that's how we define this set. I didn't mention this. Okay. So
for things in it than the parent. That's the order.
Sorry, can. Oh, you mean for this branch?
Previous slide. Did I?
So
as J as the extra.
Oh yeah, so we just define the child for a vertex. Yeah, in this way. So if you have a vertex, then you define all the possible strings. So these are the child for this vertex. So as you can see for this example, so you can see for the 1, you have 2 children, so 2, 1, and 3, 1 as 2 alternating string. And the S empty is just the root for this tree. And the branch for this tree at index 1 is just this red part. So you just remove all the 1 in index from right to get this branch. So as you can see, this is the way how we decompose a tree. Always, given a tree, you can always decompose it and to get a very simple tree, which just has 1 root and some children. Then later we will use this structure to define the K transform. So the main construction is this composition of the trees, which is the operator structure we will introduce later, where we can define the tree composition for the T1, T2 up to Tk with respect to another tree T. So here you need to guarantee that you have K trees. Then the first tree we had the number of vertices at most is just K. In this case, this map is mapping this branch of trees to another tree with the indices as the sum of N1 up to Nk. So this tree composition is defined in this way, where you just replace any string in this tree T. So you see you have a string like this. Then you, for instance, for the I1, you just replace this I1 index by any string in the Ti1 tree, which is one of the tree in this T1 to Tk. But you need to do some shift to make it as alternating string. I will show you a picture for this one. So for instance, if you have 3 tree T1, T2, and T, where you have this indices 1, 2. So here, which means it's N1 and N2 are just 2, and K is also 2. You can think about this for simplicity. Then the first step is to try to do the shape for the second one to make all the possible indices different from this the first one. So that's this order. So the T1 composed with T2 with respect to the T. So for instance, we can just consider it's 3, 4, and 3, 4. So that's how we compute this composition. So we first replace the indices for the T2 by 3 and 4. So then you can have alternating strings, which means these two are all the indices in the T1 and T2 are distinct. Then the tree composition just replace each label for the T by the indices in T1 or T2. So for instance, for the first one, this label is 1, then you just replace it by any string from the T1. So that's the first part. So that's how we do this composition. And also this empty is just the root.
So the edges of the original tree are left there. And at each vertex, you add one of the other trees.
Right. So for instance, if you have 2, 1 here, then you just compose all the possible indices for the T2, then concatenate with all the strings from T1. So the largest string for this case is this one. So you have 4 letters in the string. So that's just the 2, 1 composed with 3, 4. Yeah, any questions? And as you can see here, the number of the vertices are growing exponentially. You have like n trees to do the composition. We will introduce some notation for the composition, where we consider the composition inside are the same trees. So for instance, if you have n1 trees T2 and do the composition with respect to the T1, then we can denote this as T1 composed T2, since here we don't have the order for T2. So the computation is invariant. And in this case, the number of the indices, the maximum number of the indices is n1 times n2. And if you compose it k times for one tree, we denote as this one. So the T composed k times. Then in this case, the number of the indices in total should be n to the k's. Now we move back to the convolution. We want to use the transform to define the convolution of the mirrors. Thanks to the Professor Berkovich, we have already seen these convolutions before, like the Kersey transform, F transform, and the K transform. It turns out we can uniquely determine the property mirror given this transform. For instance, if you have the F transform, and we know the F transform at the infinity is asymptotically, F over Z is asymptotically 1 non-tangentially, then you can define a property mirror given this transform. Similarly, for the K transform, as long as you know the K over Z is convergent to 0 non-tangentially as the Z goes to infinity, then we can determine the property mirror. So in other words, we can define the K transform, then once we define the K transform, then we can define the property mirror. So that's how we define the free convolution of some property mirror. That's the main theorem from our work, where we claim that there exists some unique function from this tree n times the property mirror to another property mirror, which is defined by the following iteration functions with respect to the K transform. So we know how to define the K transform for the property mirror. Then you can see the right-hand side, you just try to decompose this tree based on its branch. And iteratively, you can compute the branch of this branch, J, then to simplify this tree. So that's, so you can think about this, this is as a function from the space of this to another probability mirror. So that's you define a functional space, and this equation is a function from this functional space to another functional space. So this theorem is saying we have the existence and uniqueness for this property mirror. And to prove that, we just need to have a fixed polynomial. Yeah.
So what does it mean? Point 3 continuous with T.
Oh, so yeah. So sorry, I didn't denote that, but here we actually need to add equate a metric for this tree. So we have this T first. So for this tree n is a compact set. So it's just the inner product for the the product for the 0, 1 point. So it's a compact set. and we can create a metric for this space, which then we can have this continuous for this first tree part. Thanks for that.
How many, what's the set of trees on n elements? Is that a finite set or limited set? Yes. Oh, n is the number of labels per vertices. Right. Okay.
The set of 0, 1 for the input.
So it's a Cantor set.
So that's the main theorem, which means we can use this equation system to define the K transform of some probability measure, which is a tree convolution for this mu1 up to mu n in this way. So we can use the K transform define this probability measure, which is denoted as this tree convolution. And the proof is based on this fixed point equation theorem by Aaron and Hamilton, where if you have a Banach space, and if you know this map is contracted, then you have unique fixed point, and for any x, the iteration is converging to this point. And then we just need to consider this as an element in this Banach space, then to do the contract to check it is a contraction map to get the fixed point equation.
So then can you give some example
for this tree convolution? So the first one is the trivial one, which you just consider the tree with only the root. In this case, you don't have any branch. So then this Q mu, this K transform is just 0. So the tree convolution is just what if we have just roots and some children for this root? Then in this case, it's corresponding to the Boolean convolution. Since if you consider any branch of this tree, that's just empty. Right? So for any children of the roots, you don't have any other branch. So in this case, you can compute the equation we mentioned before in the theorem as a sum of the K transform of mu J and compose with this one. And the second one just 0, so you have just the sum of the K transform. This is just recovering the Boolean convolution. And also here, this is commutative, so we can just write in this way to denote the Boolean transform. This is first studied by Schwanker and Vorandi. And also this is correspond to the addition of the K transform. So this is the simple example where you just have sum of K transpose. And the other one is the orthogonal convolution, where you consider a tree which has just 1 and 2, 1. So in this case, if you compute the previous equation, then you have this K mu1 composed with Z minus K mu2, which is just the K transform composed with F transform. So this orthogonal convolution has been studied by Lanzowski. So if you check these two, you can see the first one is the sum of the K transpose. The second one is the composition of the K transform and with a Z minus K transform. This is actually the two components for the equation we mentioned before. Using this, we can see any tree convolution can actually be written as this way. The outside is just the Boolean convolution. Inside is the orthogonal convolution with another tree convolution with respect to the branch of this tree. This is very useful for the computing. For a finite tree, in this case, we can use this Boolean convolution and the orthogonal convolution to simplify this tree convolution and get to compute the convolution. And this is a generalization of the free convolution case. Some other example are just like the monotone convolution. Using the equation we mentioned before, we can have the F transform for the monotone convolution as a composition of the two F transform. Also, as I mentioned before, the T2 free is actually corresponding to the free convolution. Actually, it's corresponding in the subordination theory we talked about in the morning. And if you think about the T2 free, there are two branches for the T2 free, which is this T sub and this T dash sub, which is the branch for 1 and branch for 2.
And if you compute the branch for this one, then you will get the this part.
And also, if you compute the branch for this one, you will get the T sub. So then this gives us a fixed point equation, which is defined in this way. So the first one is just how we decompose the T2 free with respect to these two branch. And second one is the fixed point equation I mentioned before. So if you consider the branch for this one, you get the second T dash sub. Okay. Using this, we can get the subordination equation system to compute the free convolution. I have to quickly. Yeah, so here, this is the graph for this tree convolution corresponding to some classical non-commutative. Also, as I mentioned before, this tree convolution has an operator structure, which is defined in this way. So if you have the convolution for this composition of the tree, which actually can be deduced to this way. So you can first consider the convolution for T1, T2, and Tk, and then do the convolution for the T. That's the operator structure for this tree convolution. And using this, we can actually find out the property for the free and Boolean and the monotone convolution. For instance, for the free case, if we consider the T2 free and a very simple tree which just have a root and 1, then you can figure out this composition has this following relationship, where you can sweep these two trees, which implies that the free convolution is associative. And also, using this, we can find out the permutational invariant.
And this can be done for the Boolean case and other monotone case.
So that's why the tree convolution and this operator structure is very important to understand different independencies. So the last part, I want to mention some limiting theory.
Since we have already defined the K transform for any operating pattern,
then we can think about some limiting theory. As Professor Bokovich said, taught us about the limiting law or the central limit theory. We are using this paper by Bokovich and Pata and Yang to study some limiting law with respect to the infinitive divisible distribution and the stable laws.
The first limiting theory
we have is if we know that mu L, a sequence of probability error, which has a limit with respect to the Boolean convolution to some probability error mu, then we can claim that we also have the corresponding limit for the tree convolution, where here we need to use this composition to define the summation. So this is a little bit different from the free convolution and Boolean case, where you just take like n mu L to do the summation. Here we need to take this convolution, which is exponentially increasing. And this limit is some probability error we define as the BP of this mu and corresponding to this tree T. So this BP just stands for the Bokovich and Pata bijection. However, here we don't have bijection. So we just have one direction where if you know the limit for the Boolean case, then we can have the limit for the tree convolution case. The question is, does this inverse work or not? Or we actually don't know for this case. And here we mentioned that this limit is some probability measure defined by this limit in the Boolean case and the tree. We actually can compute this one in the following theorem, where we can we say that this right-hand side, this limit actually exists. How do we understand that? That is just, if you choose any probability measure, you can first decompose this with respect to the Boolean, and then do the summation with respect to the tree convolution. And this limit exists, and it's just the same as the limit I mentioned before.
Oh, sorry.
N of t is just the number of the children for the root. So that's the layer of the tree. So we need to guarantee this N of t is larger than 1. Otherwise, this is a trivial case. We cannot have the limit. And also, this limit is actually convergence uniform on some compact set. So let me also, we can get some central limit theory, where if we consider some probability measure with mean 0 and variance 1,
then we can claim that this tree convolution with normalization n to the negative k over
2 is converging to the probability measure, which is mapping the central limit theory for the Boolean case to this tree T case. So for the Boolean case, this central limit theory is for the just for the Bernoulli distribution. So then we're just mapping this to the tree T case. And for the Boolean case, free case, and monotone case, this central limit theorems has been studied in many papers. Here we actually generalize this for the tree convolution case. Once we have the,
Once we have
the central limit theory, we can think about the stable law for the general probability distribution. But here, actually, we don't have a very well-defined stable laws for this tree convolution, but we can define some limiting measure in this in the domain of attraction. Sorry, I didn't define this set, say alpha theta, but that's just the domain of attraction for the classical case or the free case. So alpha and theta are just the parameter, and alpha is the stability index.
we actually know
this domain of attraction in the free case, Boolean case very well. And we also know what's the stable law for this domain of attraction. And we know all the regularity for this stable law. Our idea is just try to map this stable law to the tree case and to see if we can get some limit. And the final result is just saying for any probability measure in this domain of attraction, we can have this limit for the tree case where we just map this stable law to the tree case using the map we defined before.
and this is also
Converging uniformly on some compact set. The open question is, can we define the stable law in this T-free case, which actually we don't know how to define this. Since you can see here, we need to do this composition, which is not the sum of n variables and takes the average. It's exponentially growing of the number of index.
Then I just want to mention
some simulation. We can actually, using the limiting theorem we mentioned before, to compute this probability measure from the Boolean case to the tree T case.
So we know this new alpha theta very well.
We know the K transform for that, F transform So we can compute this right-hand side since we have the equation system for this tree convolution of the K transform. So we can use this limit to approximate this one as K very large. So in this way, we can get the K transform and the Cauchy transform. Then using the Zhejia's inversion formula, we can get the density function for this probability measure. And for instance, if you consider a tree, a finite tree in this way, we can compute the Cauchy transform, the inversion of the Cauchy transform, and to get the approximation of the density. So here we just choose K equals 6, and 3 is just the number of children for the root in this case, which is just 1, 2, 3.
And we choose this ipsilon very small and to recover the density.
In fact, we cannot choose a very large K, since, as I mentioned, the number of indices are growing exponentially. So for the computation perspective, that's very hard to generate this tree composed K times as K very large. So that's some computational issue. But for the K equals 6 and K equals 7, we didn't find any difference, so we think it's convergent. But that's just some numerical experiments. And here are some simulations.
So as you can see here,
Theta equals 0, you have some symmetric distribution, but sometimes you will have some several minimum points. We know that for the Boolean and monotone case, you will have either unimodal or bimodal density for the stable law. And for the free case, we have the analytic density for the stable law. But here we actually don't know what's the characteristic for this limiting law. And if you add the non-zero theta, then you will have some shifting, which is not very regular in this case. And also, if you consider alpha is smaller than 1, you will have something like that. We know for the Boolean case, the stable law, if alpha is smaller than 1, it's possible you have some singularity at 0. In this case, we can find out, we can also have singularity when alpha is very small, but some alpha you will have, you don't have singularity. And we don't know how this correlated with this tree structure. That's some simulation. So here are some open questions. Yeah. So the first one, as I mentioned, so there is some numerical issue. We don't know the convergence rate. And second one, as the pictures showed, we don't know the regularity for this limit. How does this connected with the tree T and the parameters? And the last one, if we consider the operator theory, can we try to define the T-free independence from the unbounded self-joint operators, which we actually don't know how to define that. So that's some questions we want to ask. Yeah.
Are there any quick questions?
So if you take your tree to just be the maximal tree, does that convolution correspond to anything familiar, or is it
maximal tree law?
so that's just big convolution.
So the Tn free we defined here is actually just the free case. Yeah, but the largest one. So if you consider all the possible alternating strings, then that's corresponding to the tree free convolution.
So this BP map continues?
Right. So we can find out that it's continuous. I mean, continuous. So for the limit now, we know that it's uniformly converges to
this BP map. But if we give this BP map, we actually don't know whether it's continuous or not. So there is a exchange of the limits, which I'm not sure for that.
For example, you don't know if it's continuous with T?
Yeah, we didn't prove that.
Done.
You know, there's a way to rephrase the map to be in terms of cumulus.
Oh,
Yeah, for in the paper by Jack and David, they
actually consider the bounded spotted mirror.
in this one you have the
cumulant and moment correspondence. And for some specific tree, like the regular tree, then you have some clear formula.
Yeah, it's just a technical context that you want to be
actually in the balance space. Yeah, right. Yeah.
Any further questions? Someone online? Okay, so if not, let's thank Zhichao again.